Hello, welcome to another module of this course, Microwave Integrated Circuits. We are in week 5. In the previous module, I had covered the basics of resonators, and I had shown that how using simple microwave components like a shorted stub or an open stub, we can build both shunt and series resonators. In this module, we shall be using those resonators to build the actual narrowband filters. So, let us review what we did in the previous class. In the previous module, we had a shorted or shunt stub and we saw that we could improve the performance by adding a gap like this. So, the first principle of a narrowband filter is that if we have series resonator in series or shunt resonator in shunt, this gives rise to a band pass filter. And if we have the converse, that is whenever we want to design a band pass or band stop filter, we have to keep this in mind. Now, the filter, the resonator that we had discussed in the previous module using an open stub coupled with a gap, that is an example of a series inductor. That can act as a series resonator or a shunt resonator depending on the frequency. But say we are using it in a frequency range where it acts as a series resonator. So, in that case, how do we make it use it as a filter? So, let us see how we can make a band stop filter using that resonator. If we have a simple transmission line like this with a filter with the gap couple open circuit resonator, say the characteristic impedance of that open circuit resonator is Z1. Then this is a series resonator in shunt, hence this whole configuration will act as a band stop filter. Now, an even better version of this is to have two two resonators. Now, if we could have a series resonator, see, in a band stop filter we need a shunt resonator in series or a series resonator in shunt. So, we saw how to implement a series resonator in shunt. Now, if we want to do the other way, that is, we want to implement a shunt resonator in series, then that becomes a problem, because shunt resonators using, say, an open stub is difficult to realize. Why is it difficult to realize? You see, an open stub resonator always will have one end either open, it has to have open, since it is an open stub resonator, it has to have this open, and the other end it can be either directly connected or gap coupled. Now, while this can be easily realized in shunt, because in shunt this end will hang from the circuit, but in series it is necessary that something at the other end is connected, which is not possible because this is an open shunt, open stub, it has to be open. So using an open stub gap coupled resonator, it is not possible to implement a shunt resonator in series. It can act as a shunt resonator because it can for certain frequencies give high impedance, but it won't be able to, but since it cannot be connected in series, hence it cannot be used as a shunt resonator in series. So that is one fundamental limitation. So now then coming back to this circuit that we discussed a few minutes ago, if we have to use another resonator, we essentially need a circuit, a shunt resonator in series. Other way of doing it is we have two open stub resonator, gap coupled resonators in shunt like this. With a lambda by 4 distance between them. Since lambda by 4 implies a quarter wave transformer, what this does is, because of the presence of the quarter wave transformer and the property of a quarter wave transformer that it can invert the impedance that is connected to the other end, from this point, even though this is a series resonator in shunt, it actually appears as a shunt resonator in series from this point. Similarly, from this point, this resonator, even though a series resonator in shunt, will appear as a shunt resonator in series. So this is the way to implement a band stop filter using our series resonators. Note one thing, that series resonators are the ones that are preferred, because as I said, shunt resonators have to be connected in series. For a band stop filter, we need shunt resonators to be connected in series, which is not possible. Series connection of resonators using open stubs or shorted stubs is not possible. Open stubs or shorted stubs can be easily connected in shunt, but not in series. Hence, we prefer implementations where all our resonators are in shunt, whether for the band pass or the band stop. So this was something about our band pass filter. Now coming to our bands, I beg your pardon, this was about band stop filters. Now coming to band pass filters, again as I said, band pass filters essentially need series resonator in series or a shunt resonator in shunt. Since again I said a series resonator in series is not possible to implement using microwave components like a open stub or shorted stub, we will go for the shunt implementation. Now before we go, we have to note that the insertion loss of a band pass filter, suppose this is our resonator, a shunt resonator in shunt. So this is a shunt resonator in shunt connected to a generator and a load. Generator internal impedance is Z0. So this is matched to Z0 both at the input and output. Or say if we consider a series resonator in series like this. So this is the band pass case, of course, because we have either a series resonator in series or shunt resonator in shunt. It can be shown that the insertion loss Li equal to 1 upon S21 square is given by this formula. The derivation is again shown in the accompanying our accompanying slides. So I said that both for the band pass and band stop filter, we would prefer shunt implementation of the resonator. So one way of realizing it is if we have our length tuned properly of this open stub, and say the resonant frequency is such that it corresponds to the high impedance state of this gap coupled resonator, then that is an implementation of a shunt resonator in shunt, and that way we can realize it. And as I said, series implementation of this open stub is not possible. However, one thing that might be possible is without not using an open stub, but using a simple transmission line element. If we have a structure like this, and this is of length lambda by 2, with say a gap of length t, and here also a gap of length t identical. Now the equivalent circuit diagram of this resonator is like this. Now, if we want to find out the S parameters of this entire structure, then we see that we have 3 circuits, this 2 capacitors and a length of transmission line in cascade. So the S, just like we did for the branch line hybrid, the overall S parameters of this structure can be found from the overall ABCD matrix, and to find out the ABCD matrix of this whole structure, we can simply multiply the ABCD matrices of the individual components and find out the overall ABCD matrix. So, for this capacitor, series capacitor, the ABCD matrix is given like this. Where this XC is equal to, or if we are using the normalized ABCD parameters, then this will be like this. So then the overall, the total, if we come back to our overall band pass filter where all 3 elements are in cascade, then the overall ABCD matrix can be calculated from the normalized ABCD matrix, that is And then finally, if we do this multiplication, the final value of this matrix that comes is now from this we can of course calculate the value of Li, that is the insertion loss, which is given by this relationship. And then the final value that comes out after doing this mathematical derivation is Li is equal to 1 plus xc square half xc bar sin phi plus cos phi whole square. Now, the resonant frequency is the frequency at which this Li is equal to 1. So, for Li to be equal to 1, this within this term within the square brackets has to be 0, and so we should have half. So, at resonance, so for this term to be 0, and from this we can get a relation now. This is a iterative equation. This equation has to be solved iteratively because there is no closed form value for this omega r. And using a simple if you just write a program in MATLAB, you can easily find out using numerical methods the value of omega r. There is to make this calculation a bit easier, this Li can be further simplified. I should write it approximately as 1 plus phi r square xcr bar into xcr bar square plus 4 upon 16 epsilon f square, and this we just I just stated a formula for the Li of a band pass filter. Now, for a band pass filter that has a lossless resonator in it, that is for which a Qu is equal to infinity, for that kind of filter, and since here we are assuming that the resonator we are using, this gap coupled series resonator that we are using, is lossless, hence Li can be written like this. Now, comparing these two equations, we can obtain an expression for QL as phi r xcr bar upon xc. Now, xcr bar, xcr, this is the value of x, c, that is the capacitance, that is the value of the reactance of the series capacitance at the resonant frequency. So, then QL comes out to be equal to this, where phi r comes from this equation that we had earlier derived. Phi r comes from this equation, and I beg your pardon, phi r comes from the solution of this equation, this equation involving sine and cos. So, phi r is equal to phi minus tan inverse 2z0 by xcr. So, in summary, what is initially given is the loaded Q factor that you have to achieve. You are given a certain resonant frequency and the loaded Q factor that you might have to be achieved, or you might not even be given the loaded Q factor. You might just be given the 3 dB frequencies. If you know the 3 dB frequencies, you can find out the value of QL, and then once you know QL, you can use these equations that we just derived to find the values of to design the resonator. See, if you plot this equation, this XCR or the normalized XCR, so on this plot the x-axis is the XCR upon Z0 or the normalized XCR, and on the y-axis we have this QL. So this graph represents this equation. Now suppose you have been given a certain QL value that you have to achieve, then you can find out the value of this XCR upon Z0 from this graph. This XCR upon Z0 is by the way, from this XCR by Z0 value that you obtain, you can find out the value of C, that is the capacitance that you have to connect in this gap. So the remaining thing that is left is to find out the value of this Z0, and that Z0 can be found out from this equation. So once you know XCR upon you know C, you can calculate the value of Z0 and the L. So here is an example of how we can solve this equation. So in this example, you have to design a filter at 2 gigahertz, and the 3 dB frequencies are at 1950 and 2050 megahertz, and Z0 is equal to 50 ohms. First you find out QL from this center frequency and the 3 dB frequencies, and using this chart we find that XCR upon Z0 using this value, for this value of QL is 5.25. So you know XCR upon Z0, then you can find out XCR and C, and the exact line length, that is beta RL, can be found out from this this value. We know XCR upon Z0, so we can plot, we can find out phi r, and since phi r is equal to beta r upon L, so from here if we know the value of beta r, then we can find out the value of L. So just to summarize once again, first we find out QL from the given conditions. From that we can find out XCR using these two equations and this plot. This plot is basically realization of these two equations, and once we know XCR upon Z0, we can find out C. Once we find out C, we get one component of our design, and then using the value of XCR upon Z0 we can find out phi r, and from phi r we can find out beta r and the length of this intermediate section. So in summary, this is how we in this module we covered two specific designs of a the first one being that of a band stop filter using a shunt resonator, and the second one of a series of a band pass filter using a series resonator. So in this in the next module we will see some further implementations, further types of filters that are used commonly. So for this, so one thing that I want to, before ending, I want to impress upon you is that if you are using open or shorted stubs as the resonator, just pure open and shorted stubs as a resonator, then you have to connect them in shunt. If on the other hand, you are using a length of transmission line which can be connected on both sides, as we saw for the band pass filter, then you may use a series resonator. But if you are using a purely open or a purely short resonator, that cannot be connected in series, and it has to be used in shunt, whether you are designing a band pass or a band stop filter. Thank you.